I'm Neil Rhodes. This is CS 152, which is neural networks, which I like to think of as deep learning, right? Neural networks entered the catalog, or at least the current version of the catalog, in 2009, and there have been a few changes since then. Kind of a lot more popularity, a lot more applications, and so on. So the course description in the catalog really doesn't reflect reality of what we're going to be talking about. Okay, but we're doing good things. Right? I am recording both audio and video, which I will put together into put it up on YouTube so that there will be a record of the lecture. However, I have had technical difficulties in the past and imagine that there will be technical difficulty in the future, so don't not take notes assuming that you can always get it in the video, okay? Because the one time you really need it, it won't be there, if that makes sense, okay? I would appreciate if you guys are actually using it. That's useful information for me. I will certainly ask later on in the semester, but it's a pain to do, so if no one finds it useful, I will stop doing it. Questions so far? All right, so these lovely cards with your name on it are great for me trying to remember your names, but also is what I'll be using to call on people. So when I ask questions, I normally won't just open it up. I realized pretty late in life, once I started teaching, that there's often someone in class, and I'm not saying there's none of them here, I'm sure, but there's someone in class who tries to answer every question and often knows the question too. And I realized when I taught one of those, oh wow, that was me. I must have been really annoying. And so to just make sure that everyone gets a chance to answer questions, I will just go around and shuffle these at the beginning of the lecture and then go ahead and call on people, okay? And unfortunately for a while, I'm gonna be saying a name and looking around like I have no idea where you are. The only reason for that is because I have no idea where you are. I'm working on it though. We have some handouts. So there's a syllabus, and we can just pass that around, and also just a table of Greek mathematical symbols. So here, my hope is, you all know your Greek symbols, rhos and kappas and sigmas and lambdas, because we use them a lot. And the things to know about them are both their names. Probably the most important thing is their names. How many of you read science fiction? It seems like a non sequitur, I know. There are really only 2 people in here that have read science fiction much. All right, so you notice how sometimes they have those funny names, like K exclamation RV RXX. Yeah, this is a character, and I'm supposed to remember, okay? And I can't say it, and so I have a very hard time remembering it. So I get annoyed at science fiction, things like that, okay? So similarly, if you're looking at some sort of a math equation and you have a symbol like this, if you don't actually know the name of it, it's a lot harder to work with than if you know it's a lambda and you can say lambda. So important that you know the names of the Greek symbols, and also important that you can actually write them. So we will have a quiz on Monday about that. My hope is you all know it right now. Great. If not, there's your cheat sheet. The one that says not used so often are ones I don't use so often, and so they won't be tested on and we won't be using them. Questions on that? Okay. The course website is at cs.hmc.edu/cs152. All right, it'll actually forward you to the correct address, but easy enough to remember. If any of your CS classes don't have this very short link, tell them to make it, because it seems very useful to me to have that. The syllabus, let's go through and look at that. So to begin with, just a distinction between how this is described in the catalog and how we're actually teaching it, in the sense that we're going to be talking about deep neural nets, which did not really exist in 2009 at the time the course description was done. So basically, we're going to be learning about neural networks, deep neural networks, applying those to image processing, applying those to natural language processing, and learning kind of both the theory and the practice of it. Okay. We will be using Python, which is what I would say most data scientists, machine learning practitioners use. And we will be using TensorFlow, right, which is from Google, along with Keras, kind of a higher level interface to that. We'll be using TensorFlow 2.0. There are pluses and minuses of that. PyTorch is also very nice, but this is what we'll be using. Okay. We have Piazza. If you have any questions, try and post to Piazza, okay? And in general, post public questions rather than private questions, because either your question is probably of general interest, or some other student may be able to answer it in a more timely fashion than I can. If there's truly a private question, then yes, mark it private. Okay, something about your grade or something else makes sense. But when is such and such a homework due? Make that a public post. The grading is, so we'll have homework. I'll look at the schedule in just a moment. Basically, it's once a week due on Mondays. Okay. The lowest one is dropped, so that kind of takes care of you running late on something or not being, just needing any time, use that lowest one. Okay. There we'll have in-class quizzes as well, starting on Monday, which will be the simple Greek symbol quiz. We have then programming assignments, which is 30%, and then 2 take-home midterms and a final. The final will be comprehensive. The midterms will be covering their portions. Okay. I don't grade on a curve, so it's just a flat 90, 80, 70, 60, with pluses and minuses thrown in as seem appropriate. I may drop the requirements to reach a particular grade at the end. I'll never raise it. Okay, so if you all get 90s, you'll some version of a 90, you'll get some version of an A. All right. The homeworks are not graded for correctness, but for effort, to make sure that you actually worked on them. They're due at 1 p.m., so before class. What I find is if it's due like at the beginning of class, people will be working it to the last minute and they'll be late and all sorts of things. So it's due at 1 p.m., submitted through Gradescope. Anyone not used Gradescope? All right. Yeah, okay, so if you have questions, let me know. If you are creating your homework electronically, then it's easy to create a PDF for it and submit it. If you're actually going to and I'll pass out homework later today, if you're going to just fill it out on a sheet, then you're going to need to scan it. My understanding is the student printers all have a scanning capability, so you can email it to yourself. There are instructions here. Questions on that? 2 textbooks. So let's see, this is, I would say I talked about sort of theory and practice. This is more the theory side of it. Okay, so neural networks and deep learning. This is 2000 and I think it's 19, I believe. So pretty darn new. No, 2018. And then deep learning with Python. So deep learning with Python is more the practical version of it. The author is the creator of Keras, which is the API basically that we're going to be using on top of TensorFlow. Okay, so lots of good practical stuff here, as well as some interesting and good theory. It's just not as in-depth as this one. This one is fairly weird to me in that the first chapter covers everything that you could want to know about neural networks to a surprisingly deep degree. And then they do come back to it. But don't worry that you read that introduction and feel completely overwhelmed, because there's a whole lot there. Collaboration. I'm just going to say that you're all bound by the Harvey Mudd Honor Code. Do read through this. Basically, any work you submit, if it's not all yours, you need to notify me of that with your submittal. Okay. let's see, Piazza, we talked about my office hours currently are going to be basically after class, Mondays and Wednesdays, and I'll just hold them in the cafe because that's convenient and close. If you need to meet me privately, just let me know, and we'll either go to my office or walk off. And then I also will have office hours on Wednesdays before class. Questions? Yes?
Can you clarify between homework and assignments?
Sure. Homework is not graded for correctness, but graded for effort that you have actually engaged with the material. Assignments are they're all programming assignments. So they're all going to be stuff done in Python on a web interface for this. So anyone heard of Google Collaboratory? So that's what you smile, kind of unhappily. So happily or unhappily?
It was used in physics lab, so
okay.
No.
Neither way.
Yeah.
Neither happy nor unhappy. Okay, so anyway, that's what we'll be doing. So it's basically a machine instance that has a GPU, which will be nice for what we're doing, that's free, and working with Python notebooks. So we'll talk more about that. I think it's next week. Other questions? Did that answer the question about the distinction in spin, right?
Yeah.
Okay. And the programming assignments, let's look. There are a total of 6 of the programming assignments, and we've got 10 homeworks. So this, yeah.
Oh, are those parent assignments or are they individual?
They're individual. Your name?
Jacob.
I never got asked that before, did I?
No, I can't.
Okay, that's good. It just means, that's good. So Jacob, all right. Yeah, they're individual. So basically the homeworks get passed out on Wednesdays. They're due on Mondays. We'll have a quiz at the beginning of class on Mondays. Assignments are due about every 2 weeks, and you've got about a week and a half, although I'll probably post them earlier so that you have them available. But in general, well, I guess it's not really a week and a half. It's a week and 1 day, but yeah. So, but I think they're very doable in that time. All right, questions? Okay. Some background on me. So I guess a jack of many trades. So I went to school at UC San Diego, undergrad, left for a while, came back to grad school, dropped out of the PhD program to start a company, never went back. So not Dr. Rhodes. Prof. Rhodes is fine, Prof. Neil is fine, just Neil is fine too, okay? And then I've worked a lot in industry and done some teaching as well. So the last industry gig was at Google, Irvine, where I was a staff software engineer. I left there, I guess it's been 4 years now. So I worked there for 7 years. And then I, as well, have taught. So I've taught at UCSD, taught here at MUD back in 2014, 2015, which was difficult because I was also working full-time at the same time, and then taught last year and this year. So operating systems, machine learning, neural networks, and then doing a reinforcement learning class in the spring. But I am usually only here 3 days a week, Mondays, Tuesdays for clinic, and Wednesdays. So it's harder for me to schedule stuff on Thursdays and Fridays. But if you need to schedule office hours on Tuesdays, that can be very, very doable. Okay. And if people need me to make permanent office hours on Tuesdays, I can actually probably do that fairly easily. Just make a Piazza posting or let me know, and I'll consider doing that. So if my current office hours just don't work. I think that's all for administrative stuff. Let's go ahead and get started. How many of you have had, taken the machine learning class? Okay, so about 3 and 3, all tentative people. So you took half of the class, it looks like. And for the rest of you, any of you had any introduction to neural networks? Okay, so even some full hands. Okay, that's good. All right, it's not necessary. I'm just curious. So one way to look at machine learning, well, to compare it against traditional programming. In traditional programming, this is a diagram from the Agarwal book that I kind of like. It's very high level, but I think it's reasonable. So the idea is you have rules and you have data coming in. Really, the rules are the program, right? You write the program and it embodies the rules. But you can think of kind of the rules coming in and the data coming in, and coming out are answers of some sort, right? So that kind of makes sense, right? It roughly approximates what we do. In machine learning, we have the same inputs and outputs, just arranged differently. So we have data coming in, and we also have answers coming in. And from that, we create rules. Right? So the rules that we create are normally some function. All right, we'll call it f for a function. And I'm going to throw in a theta here, just saying we're parameters, right? These are the parameters to the function. Let's say we were learning a function which is a line. These parameters might be the slope and the intercept. Okay, so we have all possible lines in 2 dimensions that f could be, but the parameters specify which actually line that we're looking at. So once we've got this function, so first off, this is not by itself useful, right? To take in answers and data and come up with rules, unless we do something with these rules. So this, coming up the rules, is the training that we're doing. And then what do we want to do? Rory?
Testing and modifying.
Okay, so testing makes sense. So we were going to want to train. We are going to want to test. Let's say we're happy. We don't even know how we're going to test yet, but let's say we test. We'll come back to this later today. Then what?
Modify our rules.
Okay, modify. We're all happy. The rules are great. We've got almost perfect rules here. Now what?
We can use the rules to examine new data.
Yeah, so we want to, let's just say, deploy this and use with new data. Okay. So when we're using it with new data, or kind of like going back to this way, right? The difference is we didn't write these rules. The machine learning wrote the rules. So we'll feed in rules, we'll feed in some new data, and we'll get out some new answers. So we'll basically be feeding into this function. What the machine learning is creating is a big function, which is the rules that are coming out. So f is this function. What does it take as input? See, Brandon, your picture looked like you. Is that Brandon? Yeah. Okay. So what does f take as an input? Data. Data. So it takes data as input, and as output, Santi?
Rules.
So the function doesn't produce rules. The function is the rules, right? The function is the output of the machine learning. Say that again? Answers, that's right. So I'm going to call this x, right? And this y. So here we're passing in x and y. We're coming up with rules, which we're talking about as f. So f, right, of data is x. And it comes out with, I'm going to call it y hat. So this is approximated answers. Okay? Y hat meaning it's our best guess as to what y is. Our output that f thinks should be for this x, which may or may not be accurate. But assuming we've trained well and tested well, we hope it's reasonably accurate. what could this data be? Let's see, we're calling you Matt. No, we're calling you Matthew.
Either if I'm Matt.
I know, but I'm trying to distinguish because right behind you, you've got a, what do you go by? Matt? Matthew or Matt? Matthew? All right, you're both Matt and you're both Ben, okay? So Matt, closer. What kind of data could we have coming in here? Give me an example of something we might want to learn.
Well, if you're using like computer vision, it could be a photo maybe.
All right, so we have a photo. This is my best guess is a photo. Okay, so there's a photo. That can be input, right? This is X. Well, let's even back up a second. How would we represent this? We won't actually give the piece of paper, right? So what will we provide to the computer? To F, let's say.
Include it as some pixels.
Okay, so let's say we do some pixels. Let's say we do 200 by 200 pixels. And let's say it's a grayscale image, right? So we've got basically 200 by 200 pixels, and each of these might be what?
Like if it's grayscale, then maybe just like a number depending on the shape.
Give me a range.
0 to 10.
Okay, it's weird because we're computer people and we always think in binary. So I would go with 8 or 16. So let's go 16 because we don't want to waste bits, right? So this is a possibility, 0 to 16, or it might be a floating point number between 0 and 1, all white, all black. So we could look at it as basically a vector of 40,000 4-bit integers, right? And this is our picture. And this is what we can feed into F. So basically just feed in a vector. It could be a one-dimensional vector. We also could actually pass in a matrix, right? A two-dimensional vector there. Does that make sense? Questions on that? All right, so that's the X. She, I didn't ever meet you. You go by Susan? Let me fix that. All right, so Susan, what output might we have for such a picture? What might we be wanting to get out of this picture?
Maybe we want to differentiate between happy face and sad face.
Happy face and sad face, I like it. Okay, so let's say we're doing happy face, sad face. So as we're doing this training, we're going to be feeding in, right, that same picture. And associated with that will be what we'll call our ground truth. Or you can think of it as we're feeding in labeled data. So it's not just the raw data, but we're feeding an actual label that goes along with it. In this case, if we're talking about happy face, sad face, just true, false, I guess, right? Or we'll say 1, 0. So for this case, the input would be, so this is a 1, and this is the X here, right? Clear so far? All right, and then we might have another one. Let's say this is a training example that's a 0. So we have a bunch of training examples, our input, our correct output. Input, correct output, input, correct output, and so on. Right? We use all these, and we need to have a lot of them, to train to get good parameters for F. Right? We'll talk more on Monday, but one of the things we're going to have to decide is this F, what does it look like? It'll be very parameterized, but what kind of a thing is this? And we're going to be spending the first several weeks, actually, not using neural networks, okay? We're going to be using simplified versions of F, like linear functions or polynomial functions. And we're going to get all the rest of the training and learn all of that part. So we're going to learn how to be dealing with labeled data sets, how we're going to be finding the correct thetas, okay, the correct parameters, how we'll be doing testing, and so on. But just be aware, no neural nets for a little while. But everything else is going to be quite relevant. Okay, so we get our f of theta, and out comes a y hat, right? So now let's say, let's say we use this picture. Ideally, what would y hat be for this input once we've done the training? Jacob? Jacob. That's number 2 for Jacob. Right? It's only the second time I've gotten his name. All right.
It would be the same as y in the machine.
Ideally, we would have y hat equal to y, right? In this particular case, where this was part of the training set. Ideally, even things that weren't part of the training set would be correct in the sense that if someone actually looked at it and assigned a label, it would match what was coming out of here. In reality, this might not be perfect. So if this isn't perfect, we could actually, back up a second. We get to design our f, okay? There are going to be parameters associated, but we design f. We get to design what it takes as input. In our case, we're going to take a 40,000 vector of 4-bit integers, and we get to decide what output is. One possibility of the output would be, boy, those are very bad looking braces. That's a good looking brace. It could be binary output, 0 or 1. Okay. The problem is we lose a little bit of information there. Let's say I ask you to look at a picture and tell me whether it's a dog, okay? No, let's say a dog. Let's say it's a dog breed, okay? Is this a Vizsla or is this a Chihuahua, let's say, okay? And you're not very familiar with those. So you could say, let's say, yes, it's a Vizsla, but I'm not very confident. Versus, I know my Chihuahuas. And so if you ask me if this is a Chihuahua, yes, it's a Chihuahua for sure. How could we capture that level of uncertainty? Okay, Ezra, I know no, you're not Ezra because you're Mo. All right, help me out, Ezra. All right.
Capture the level of uncertainty.
How can we capture the level of uncertainty? Let's say for a face. Let's say we've got a face that's coming in, and it's like, sorry, that's definitely happy. That. Okay?
Probably want to set a scale for how happy.
Okay, so how happy, or possibly how sure you are of happiness, which might be similar. If it's a giant grin, you're pretty sure they're happy, and they seem to be very happy. So how could you change the range, the codomain of your function from binary to something that could represent?
Like sort of graphical, like a list of lists type of.
Say more. Like you could have a sad, very sad, indeterminate, happy, very happy, kind of like a 0 to 7 scale or something? Or-
Yeah, sure. Or I was thinking maybe you can set different parameters, like maybe you have how happy on one axis and like how sure on a different one.
Oh, I see. Yeah, you could do that. And if we wanted to, we could construct something like that. We could have a situation where we're trying to measure not only just whether they're happy or not, but how happy they are. And it'd be nice to have some certainty on that as well. Here, I want to keep the problem still binary, happy or unhappy, and yet I still want to capture this certainty level. Max?
Yeah.
Any thoughts?
two values, like one that says what it thinks it is and one that says how certain it thinks it is.
Okay, and how would you represent the certainty?
Could represent it just as another like eight possible values.
What if we wanted to make it continuous?
If you want to make it continuous, you could do like from 0 to 1.
0 to 1, and that might represent how certain you are. Or another way to think of it is the probability that it is that, right? So you could look at, so instead of making it 0 or 1, well, let me describe your way and then describe a simplification. Okay, so here we would have two values. So kind of what is the label, and then we could also have a certainty from 0 to 1, right, as a range, 0.0 to 1.0. And so if we were pretty undecided, I guess we would have like a certainty near 0, and it would hardly matter which label it was, because we're not very certain of it, right? It's another thing we could do if we only have two labels. So we could just say probability that X is happy, or that it's a happy face, is really what it is, equals Y hat. So in this case, if we can't tell, what would this value be? Anyone? 0.5, right? 0.5 just says, I don't know. And 0.95 would say we're pretty certain they're happy. And 0.05 would say we're pretty certain they're not happy. Right? And when we're actually using this, we've done our training, we go to deployment, we get a brand new face, and we get a number that comes out. Well, if it's greater than 0.5, we'll say it's happy. And if it's less than 0.5, we'll say it's unhappy. And if we want, maybe we could say if it's greater than 0.75, we'll say it's happy, and less than 0.25, we'll say it's unhappy, and in between we'll say, I don't know, I'll throw that in a different bucket, have someone else look at it or something. Does that make sense?
If it's so that the two categories that they can fall in, if they're similar in some way, so that you can be certain of both, like more certain of both, so it's binary, but like happy and like excited or something like that. That was binary categories. So you could
Two binary categories?
No, just saying like, so if it was happy and excited, where you could be certain that you could be pushing towards certainty on both, but certain of neither.
It sounds like you're talking about having, and correct me if I'm wrong here, that there would be two axes, happy and excited. Am I right or not?
Yeah, I guess it would be.
Yeah. So we could have happy and excited. And one thing we could do is just do the same thing for each of them independently. The probability they're happy, the probability that they're excited. We have a lot of options. So as we are doing machine learning, one of the things we get to decide is what's our input look like. Right? That's what's the structure of our input. Is it going to be 200 by 200? Is it going to be bigger? Is it going to be smaller? It's going to be different sizes. Are we representing it as a one-dimensional array, a two-dimensional array? Are these 4-bit values or floating point numbers? We are in control of all that. Now, we may be restricted in some ways by what we have access to, right? We are also in control of the structure of what's coming out of F, because we're sort of designing the structure of F. So we get to design. Structure of X, the structure of Y, the structure of Y hat, which in this case is slightly different than Y, right? Because Y we know is just 0 or 1. And whereas we're saying Y hat is a range between 0 and 1. And the structure of F. Okay? Where there's a lot of F that's going to be undetermined to begin with. We'll be using, to begin with, linear functions. And there, what we're leaving open is, what's the slope, what's the intercept? So that's what we'll learn. But we are sort of predefining a lot. We're constraining the space of possible functions based on the input, based on the output, and based on what calculations actually get done in there. So what representation, what we can represent in F. Questions right now? Ben?
So with this the way it is, for the data you would pass in y hats, you pass in like a 0.8 if you're like 80% sure it's happy.
So for our data, so y hat is always output.
Right.
Okay?
But in the machine learning, yeah.
Here, y. So the hat is always going to be our calculation, our approximation, and y is the truth. Okay?
But for to capture the uncertainty of like how certain you are that that's the classification.
So there's two questions we're going on. When I was talking about certainty,
Okay.
I was talking about the certainty the function has,
Okay.
as opposed to what I think you're talking about is the labeling. How certain were we when we actually labeled it? So we got a bunch of pictures, and we went through, and we looked, and we said, is this happy or not? I'm not sure. Okay. One could also capture that uncertainty. A lot of times one doesn't. That they just come in labeled, and you can't tell whether they were really sure or kind of unsure. Okay. Or another way to look at it rather than certainty and uncertainty is maybe what we had is a labeling done by 3 different people. So Anisha and Willow, and it starts with a J, and is it Jacob? And Jacob. All right, so they are, right, I'm giving them 3, the same picture, and they're independently labeling it. And Anisha says, and they're not listening,
Happy?
and Willow says,
Happy.
and Jacob says sad. Okay? And so for this picture, there is some uncertainty because there was not multi-observer kind of agreement, whereas a lot of other pictures might be everyone, all 3 of them agree. A lot of times we don't capture that. One could, though. And the way one could capture that is just y is not binary. Y is actually a value between 0 and 1. So this is a picture that like is 75% sure it's happy. That's what I want you to learn. That would work fine. That is the distinction between designing the structure of y versus designing the structure of y hat. Okay. All right, let's look at another diagram from the Agarwal book. So is this difficult to see if I put it over here? Does that work? All right, so we've got F. F gets fed in X. What comes out of F? Y hat. We just always know X's go in, Y hats come out. Y hat. My diagrams are kind of boring. I basically use squares and occasionally a circle randomly. Okay. What else is coming into F? What controls how F works? The parameters. What do we call those? Theta. So these are theta, which I'm going to say are the parameters. Okay? And when we talk about learning, this is what we're learning. We're learning the thetas. We designed F. We designed how X is going to come in. We designed how Y hat is coming out. We also have Y coming in. I guess we'll make it look like this. Y. And these guys, right, they come in pairs. This Y is for this X. We feed these two. Hey, this is something else we get to design. An ellipse, which is meaningless compared to the rectangles. This is our loss function. This says, how close are we? Okay? How close is this Y hat to this Y? Now, if they're identical, our loss function should probably make those be 0, but we get to design that. So this gives us an overall loss. Questions so far? Mo, what is our goal overall?
Minimize the loss.
Minimize the loss. What can we change?
You can change the F.
F, as part of the training, we can't change it. Sort of outside of that training, we could say this is a screwy F. This is not going to work. We're going to have to go do a new F. But as part of our machine learning process, where we're just sending the computer and saying, go, what on this diagram do we get to change?
So after we already have our F, we're trying to change certain values to minimize the loss.
Let's say here's what we do. So we'll make it more concrete. We have let's look at an example. So an example might be, we have I'm going to make it kind of X's and O's, okay? We're trying to just differentiate these X's and O's. And somehow we get given some data that says where these X's and O's are, and we're trying to separate those in some way. And we're going to use a linear function for this. So our linear function is going to start out, we know it's linear. So how many parameters do we have in theta? 2? Yeah, we have our slope and intercept, let's say. And to begin with, right, ignoring the data, because we haven't really seen the data, what should we initialize those to? We don't know. We'll just make them random, right? Like let's say there, right? That is our initial slope and intercept. Is this very good? This does not separate the X's and O's very well. So what is it we're trying to make better? The parameters. So our loss is going to go into an optimizer. And an optimizer updates theta to minimize, not to minimize, to reduce the loss. And we are going to run this many times on lots and lots and lots of data. And the theta is going to get better, we hope, it's going to get better and better and better and better until eventually, and we'll see this on Monday, an example where it might go like that. And so we've updated the slope a little bit and the intercept a fair amount in order to get something like this. So it's a successive approximation that we are doing, starting with random parameters, taking some input, calculating a y-hat. Right, if we take random parameters and calculate a y-hat, is this going to be very good? There's no particular reason to think it is. And so we'll have a high loss compared to the y. And so we will go through, we'll run through the loss function. Yes, we have a bad loss. The optimizer will make some usually very small changes to theta to make them slightly better. And as we go and we go and we go, the loss over time will decrease. Right? Questions on that? So what we're going to be spending the first 3 weeks on is everything except the F. Right now, we're going to be using linear and polynomial Fs. We're going to learn all of the rest of it. The nice part is we're going to be able to visualize our y-hats, our x's, our loss function, our optimizer in a domain in which we're very familiar. Then we're going to say, okay, linear and polynomial is just not very powerful. What if we had a more powerful F here? What are we going to use? Neural network. Okay? That's the plan for the next 4 weeks, let's say. So within 4 weeks, we'll be into neural nets. But we're going to learn all about the rest of this. So when we are designing, we have to also design, is this readable or not? Okay, so let me switch to white, which I guess is more readable. So we're designing the structure of x, the structure of y, the structure of y hat, the structure of f. The structure of f determines what our parameters, what the parameters are, not their values, right? But what the parameters are. What else, according to that function, or sort of according to that picture, do we get to design? Daniel?
Yeah.
Okay.
The loss function?
Loss function. We get to design the loss function. And you, Jacob, Josh? Josh, what else do we get to design?
The optimizer.
Yeah. And when I say design, it's sometimes just choose, right? The optimizer. These are all choices we make. We go through, once we've made all these choices, we can run and let our machine learning chug, right? For, depending on the problem, right? 30 seconds, an hour, 5 hours, 5 weeks, on one machine with 8 GPUs, on 10,000 machines if we're Google, right? And then at the end we look and see, well, along the way we also look and see how we did. But if we didn't do well, then we can change some of these. The only other thing we get to design we get to design our data set. Right? Maybe we decide we need more data. We're going to look at cases where we might need more data in a moment. Questions about kind of where we're going? Okay. All right, so let's look at an example. And for the time being, we will talk about polynomials today too. So, but let's say we are trying to predict house prices. Okay, so Zillow. If you ever looked at Zillow Zestimates or Z-estimates, I'm not sure how they pronounce it, but they come up with a price, and it's sort of interesting because they'll actually, in some cases these days, buy your house for that much, right, based on their estimate. For a certain sub-range of houses. Anyway, so we've got here our house price. And what sort of information might you use to determine a house price? Ben? You, Ben. I'm making eye contact with you.
Location.
Okay, so location.
Size.
Or as real estate says, the first 3 items would be location, location, and location. Size in terms of
Like square footage.
square footage. Okay, I'm going to put that one down here. But other possibilities?
Like amenities, like there's a pool or.
There's a pool. Number of bedrooms, number of baths, lot size, all those sorts of things. Well, comparable houses maybe. But for now, we're going to just look at this very simple model, which we might be missing some. Right, so we might not be completely exact in our estimate. But we're going to just do square foot to house price so that we're 2D. Okay. And let's say we have 2 data points. All right? That's all the data we could gather. So we have this house has this square footage and this price, and this other house has a larger square footage and has a larger price. If we were to use a linear model, what would make the most sense to do? Anisha.
I guess if we're trying to classify.
So what we're trying to do is what's called a regression. We'll talk about more on Monday. We want to be able to. Okay, so here's a good question. This is a great question. What's our x going to be?
Our x is going to be the square feet of the house.
So that's going to be square foot. Our y we know is a price, right? What's a y hat going to be?
price estimate?
Yeah, so this is going to be price estimate. So we could write something, of the form y hat equals, mx plus b, right, where these two are our parameters. And that's what I'm going to, and so there's no, this seems like the best thing to do, right? To have a line. I can't even write a line that went right through them, but it went right through them. Okay. What's our loss? Assuming we have what seems like a reasonable loss function. Matt. In the back, Matt. Yeah.
I imagine the loss would be the difference between our predicted prices versus the actual price.
Sounds great. So if this is our function, y hat equals mx plus b, and we have this line, what's the difference between y and y hat? 0. So it seems like we got great loss. Now, is Sally, right? Is this necessarily a good function?
Do you mean like to represent the house price in general, or just like only take, is it, okay, well not really, because you're only taking into account square foot and you only have 2 data points. But
Okay, so given we only have 2 data points, what might happen, right? We don't care about these data points, really, do we? What do we care about?
the function
The function comes, and how are we going to use that function?
to assess data points we don't know.
To assess data points we don't know the answer for. So what we really care about is data points we don't know the answer for. What we have are data points we do know the answer for. So these two are our training data set. So these are x, y pairs. Okay? And we don't have very many, which is not good, right? So it could be that if we looked at other data points, that we might have something like, I don't know, that. What do you think of that line as a model for calculating house price based on square foot? Still you.
I still don't think it's like that great, but it's better.
No, I'm going to back up a second. So, how well is this doing at predicting for these x's that we didn't use as part of our training data set? Not that well. So, if we don't have any other information, is there a better function you could use here, assuming all I'm going to give you is square footage?
A nonlinear function.
Okay, so you could have a nonlinear function. Let's say what we did is we had those 2 data points. Okay? And Sally rightly says 2 data points is not enough. We need 10, 2, 4, 6, 7, 8. It's about 10. Okay, let's call it 10. Okay, 10 data points. And so I carefully went out and got 10 more data points, right? Randomly sampled because it's important so that we can generalize. And then Sally says, perhaps rightly, a linear function is not the way to go. Perhaps we could use a nonlinear function. So we take a pause now. Okay? So here's the pause. In my first calculus class, the professor said, what is the next number in this sequence? 1, 2, 3, 4, 5, 6. We don't just jump out. And it's not obvious to everyone, okay? You can't just give it away. Okay, so it seemed like 7, right? It turns out you're right. 7. Okay, yes. Except that's not what I think. I think the next number here is actually 1, 2, 3, 4, 5, 6, 727. Okay? I'm thinking of a function. The function I'm thinking of, what function were you thinking of? Like f of n.
F of n is n.
Okay, that's not what the function I was thinking of. Here's the function I was thinking of. F of n equals n minus 1 times n minus 2 times n minus 3 times n minus 4 times n minus 5 times n minus 6 plus n. All right? So for the first 6 values of n, this is, 0, 0, 0, 0, 0, 0, and then all of a sudden this becomes, what, 6 factorial, which is 720 plus n is 7. What if I wanted this number to be 1,326? Can we do that?
Probably.
We could easily convert this. Here's how. Subtract n, so we'll keep in a plus n here. Divide this by 6 factorial. And multiply it by 13, 19? Is that right? So when n is 7, this is going to be 6 factorial divided by 6 factorial, which is 1, times 1319, plus 7 is 1326. So you can get whatever you want, right? Why is it that these seems a more reasonable answer than 1,326 from this equation? Anyone?
Function's a lot simpler.
The function is a lot simpler. Simpler? Complex. Prefer, in general, simpler explanations. Right? That's Occam's razor. And I never remember why it's called a razor, but it's not a shaving razor. Right? Occam's razor is roughly prefer simpler explanations. Do you agree with that in general? All right. Now let's come back over to here. So let's say we have a nonlinear function. Let's use a polynomial just to keep life a little easier. And let's use a polynomial. Oh, I don't know. This one was what degree? Other bin. Yeah, 6-degree polynomials. And so we had 7 degrees of freedom, right? Because there are 7 coefficients we could choose there. So we can fit any 7 data points we want with. So here, what we might do is, here's a nonlinear. I'm going to come up with a zero loss nonlinear function. Okay? So it looks like and then I don't know where it goes, somewhere out here. How well, Nick, do you think, well, how well does this do on our training set? Perfectly. Are we happy? Probably not, because if we go and look at more general data, it's probably not going to generalize very well at all. Right? The previous one that Sally had where we had just the line, it wasn't great. It wasn't great, but it generalized okay given this data, right? We still had error, but this is going to probably give us crazy error, right? So there used to be something right here that says train, right? After train was test. How can we test whether this is good or bad? Assuming we can't necessarily visualize it. What can we do to see whether this is a good or bad trained function?
We would plug in more data where we know the square footage and the house price.
So we have to have more ground truth data, right, in order to verify how good this is. Because when you have a training set, the function can get really good at learning the data, right? Like, the example would be sort of like if you had a bunch of happy face pictures, instead of trying to figure out there was a smile or not, it just memorized. Oh yeah, these pixels, I got them. This is 75% happy. And these pixels, right, I know are something else. And that's not very generalizable, right? If it sees these exact images again, that's great. But it could generalize to shit, right? So I would expect this not to generalize well. But the only way to tell is try some more data. So we have our training data set that we use for training. We will also have a validation data set. And this is used for evaluation. So if we have a bunch of data, let's say we have 100,000 instances of data, right? So we carefully went out and gathered this stuff and marked it or figured out the square footage, figured out the house price and so on. Do we want to use it all for training? No, we don't want to use it all for training because if we use it all for training, we have no way of determining how good it is afterwards. So we might say, I don't know, we're going to put 80,000 into training and reserve 20,000 for validation. Right?
Is there a general rule for the ratio that you use?
The ratio is dependent on how many instances you have. So as you get more and more, this can become a smaller and smaller fraction. But this isn't an unreasonable separation here. So, 99K and 1K would be, and 50-50 would be as well. So what we do then is we run this loop over and over again, and we look at this loss. Okay? This loss is our training loss, and we expect it to go down over time. We look at another loss as well. What's the other loss we look at? Willow? We can look at our validation loss. So our validation loss, would we expect our validation loss to be better, that is lower than our training loss? Do we ever expect it to be worse than the training loss? What about this case? If we had this case, would we expect our validation loss, right, our training loss is 0? Would we think our validation loss is going to be 0? No, it'd probably be bad, right? Our validation loss could match our training loss if we have a very, very generalizable function we've learned. It's rarely going to be less unless it's randomly less. But in general, it's going to be higher than or equal to the training loss. And to start with, they're both going to be bad. And as time goes, as the training loss gets lower, the validation loss is going to get lower. So this is the validation loss. But at a certain point, it's going to start increasing over time. So this area here is where we're what's called overfitting. overfitting in the sense that we are instead of creating a generalizable function, we're creating a function that is fine-tuned for that training data. And this is kind of how you tell. You monitor, as you're training, the training loss, which should be going down over time. It may plateau at some point. So you may have a case where it just stops and it's not going to get any better. And then the validation loss, you'll see start going up. And over time, that validation loss is going to get worse and worse. So this is overfitting. What causes overfitting? Okay, Nolan, where are you? Nolan, all right.
When you're like connecting the dots.
Okay, so what allowed us to connect the dots?
The model was too complex.
The model was too complex. We had too many degrees of freedom for our model. So causes of overfitting. Model is too rich. Okay. How can we solve that?
Simplify.
Okay, so one choice is simplify the model. What else could we do?
Cross-validate.
Back up a second. How big was this training data set?
8 points.
8 points. If we were restricted to an 8-degree polynomial and we threw in a lot more data, what would happen? So let's say we threw in some more data. What do we tend to think this is going to look like?
Well, it'll be better. It won't connect all the dots.
Yeah, it's not going to connect all the dots, and it's going to tend to kind of go, probably like this. Since it's an 8-degree polynomial, it probably has some waviness, but it's going to look linear-ish maybe if the data kind of, as we look at it, looks linear. So an alternate approach to reducing the power of the model is what? More data. So simplify the model, or more training data. These are the fixes. That's for overfitting. What is underfitting? Would you guess? Allie? It's Allie, not all of you. Allie? Allie.
Before, like, the validation, but.
Okay, so like here? Yeah. So underfitting is basically a high training loss, right? Overfitting, we can kind of look and we can say this is, how do we know we're overfitting? We have low training loss and high validation loss. That's how we tell. How do we tell we're underfitting? Say again, Ellie.
Before the validation part, or validation loss.
Okay, so what's a training loss look like?
It's like vertical.
It's high.
Yeah.
Yeah. So we have high training loss. Fixes. Rachel? Yes.
Fixes the underfitting. Keep running it.
Okay, so train more. Train longer, let's say. That's one possibility. Another possibility might be, so here's an example of underfitting. Here's some data. Let's try it differently. All right, there's some data, and we've got a linear model. change the model to add more complexity, that's right. So train the longer fixes, train longer or increase the complexity of the model. Again, complexity, degrees of freedom, and so on. Okay. Our model is just not rich enough to capture the actual data. Does it make sense? All right. Questions at this point? So this is the first introduction kind of to all this. We're going to learn, for instance, that as well as training data set and validation data set, we're going to have another data set too. Okay. But we'll talk about why that is. We'll talk in detail on Monday about linear regression. And let me now pass out the homeworks. So any last questions? Go. All right, so I will be in the cafe as soon as I clear up all my equipment. And otherwise, I will see you on Monday. So come Monday, what happens? Quiz, beginning of class. About? Greek alphabet. And? Homework due, 11 a.m. No, sorry, 1 a.m. Grade scope. 1, let's say p.m. 15 minutes before class. All right. Have a good weekend.